A computer system needs some way to keep track of the processing that is currently taking place in the processor. Remember, a 4 GHz processor can execute roughly 4 billion fetch execute cycles per second. The processor has a flags register for this purpose. The flags register is a 16-bit register in the CPU. Each of the 16 bits represents a different flag that is responsible for storing the current state of a specific thing, such as the sign of a number that's just been processed, or if an overflow error has occurred. The flags can be set to true and false. If a flag is true, the sign bit is 1, and if the flag is false, the sign bit is 0. All flags are reset to 0. Flags can be categorized as status, control, and system flags. We're going to learn about 4 of the status flags contained in the flags register: the sign flag, the overflow flag, the 0 flag, and the carry flag. Right, let's have a look at the sign flag first of all. Let's move that up there so that we can still see the picture. So what can we say about this sign flag? So the first thing that we need to be aware of is that the flags are set as the result of calculations that have just been carried out in the arithmetic logic unit. So what we can say here is the sign flag is set or reset depending on the result of the last arithmetic operation. Right, so that's important to bear that in mind. It's always set as the result of the last operation that's been carried out in the arithmetic logic unit. So let's think about an operation that would be carried out. Let's say in decimal we were doing the calculation 7 plus -8. We would know that the result would be -1. Yeah. Now, in the arithmetic logic unit, it would use 2's complement. So it would be an addition using 2's complement. So let's see what that would look like. Right, so we've got, let's put in the values at those places. So we've got 1, 2, 4, 8, 16, 32, 64 and 128. And our first number is 7. It's a positive 7, so we don't need to express it in 2's complement. We can just use it in unsigned form, and 7 is a 4, a 2 and a 1. So expressed in 8 bits, it would be 000000111, and that's equivalent of 7 decimal. Now the -8 is a different story. It needs to be expressed in 2's complement. And how do we express it in 2's complement? It's 3 steps, isn't it? First step, find the positive, flip the positive and add 1. So let's do that. I'll change my pen and I'm going to do this down here. -8, there's an 8 there. Flip it, so that's 1 1 1 1 0 1 1 1, and then add 1. So let's add these up. So 1 and 1 is 2. 2 is written 1 0, so we put down the 0, carry 1. 1 and 1 is 2, put down the 0, carry the 1, put down the 0, carry the 1. 1 1 1 1 1. So -8, let's write that in. So it's 1 1 1 1 1 0 0 0, and that's the equivalent of -8 base 10. I'm just going to get rid of my workings there. Don't need them now. Right, now I'm going to add these together because that's what the arithmetic logic unit would do. So 1 and 0 is 1, 1 and 0 is 1, 1 and 0 is 1, 1, 1, 1, 1 and 1. So this is minus 1. Now, to check it, the most significant bit here, the most significant bit has got a 1 in it, which means this number is a negative number. And you know in 2's complement, if the most significant bit has a 1 in it, then whatever place value that is for that most significant bit, it's a negative. And in this case, because it's 2 to the power 7, that means it's a minus 128, negative 128, plus 64, plus 32, plus 16, plus 8, plus 4, plus 2, plus 1, and you're left with negative 1. So that's where that's coming from. Always check your answer and be assured that this most significant bit, it's included in the value of the number, but if it has a 1 in it, then it has to be treated as a negative. So what can we say about this sign flag now for this example? So in this example, after the calculation has finished, the sign flag is set to 1, indicating the number is negative. Let's move down now and we'll have a look at the 0 flag. Now, what is the 0 flag and how is it used? Let's put in a wee note about it. So again, the 0 flag is set as the result of the last arithmetic operation. If the result is exactly 0, then the 0 flag is set, and that means it contains a 1. So let's have a look at an example of that, yeah? So if the 0 flag is set, that means that the last calculation resulted in 0. So let's have a look at a couple of things that would result. Let's do a decimal first. So say we say 20 decimal minus 20 decimal. Well, that would equal 0 decimal, wouldn't it? So how would this be carried out by the arithmetic logic unit? Well, we know what it would do. It would say unsigned 20 plus 2's complement 20, negative 20. So let's do that. So, and we'll express it in 8 bits. So 20 would be, I think I'll use my black pen for this. So 2 to the power 0, 1, 2, 3, 4, 5, 6 and 7, and the 20 would be 0, 0, 0, 1, 0, 1, 0, 0, so that's a 16 and a 4, and the negative, so that would be equal to 20 base 10, and negative 20 would be written 1, 1, 1, 0, 1, 1, 0, 0, and that's negative 20 base 10. Now, if you want to check that, because I didn't do the long way, let's just do it. So it's minus 128 plus 64 plus 32 plus 8 plus 4. 128 minus plus 64 plus 32 plus 8 plus 4, and that equals minus 20. So always check your workings if you're not confident or comfortable with the 2's complement yet. Just check it. Right, so I can get rid of that working because I believe it now. So what is the result of this? Let's add them together and see what happens. So I'll use red, put a line across, and we're going to add these together. So 0 and 0 is 0, 0 and 0 is 0, 1 plus 1 is 2, put down the 0, carry the 1, 1 plus 1 is 2, 1 plus 1 is 2, 2, 2, and we've got a carry bit. But the 8 bits that we're using as the answer, 1, 2, 3, 4, 5, 6, 7, 8, make this 0. We'll talk about the carry bit that's occurred as a result of that in a wee second. In this example, the 0 flag would be set because the result was 0, 0, 0, 0, 0, 0, 0, 0. Now let's move on to the carry bit, since that example above talks about it. Well, what can we say about this carry flag looking at the example above? We can say that the carry flag is set if the result of an arithmetic operation results in a number which is outside the representable range. That is, a carry has occurred after the most significant bit. So let's look at an example for the carry flag. And we'll do an example which is 4 bits. And in decimal, we want to add the unsigned numbers 7 and 9. Now in decimal, 7 and 9, so let's put in base 10 would be 16. But we've only got 4 bits. Now, is this answer going to be within or out with the representable range for 4 bits? So let's find out. So we'll just put in our number grid as normal. So there's our place orders for the 4 bits, and let's put in the value of each place. So that's 1, 2, 4 and 8. And we're just using 2 unsigned numbers, so it's not 2's complement. Let's start with 7. So that's a 4, a 2 and a 1, so that's equivalent to decimal 7. And 9 would be an 8 and a 1. And that's a decimal 9. So the answer, adding these together, 1 and 1 is 2, so put down the 0, carry the 1, 1 and 1 is 2, put down the 0, carry the 1, 1 and 1 is 2, put down the 0, carry the 1, 1 and 1 is 2, put down the 0, carry the 1. This answer is out with the representable range because 1, 2, 3, 4, 5 bits are needed. So what can we say about this? In this example, the result of the arithmetic operation is out with the range of representable values, So the carry flag would be set. So this is the representable range, 4 bits. This one is outside the range, so therefore the carry flag would be set, because in this instance this bit here, let me get more room there, this bit here is the most significant bit of the 4 bits. Right, now let's have a look at the next flag, which is the overflow flag. It's quite interesting. So the overflow flag. Now the overflow flag, what's different about it? What is the CPU checking for? So an overflow is said to occur when you need more bits to store the number than are available. Now, what you might be thinking to yourself at this point is, wow, that's the same as the carry flag. But there is a rule attached to the overflow bit. So let's put the rule in next. So the overflow rule is if two numbers with the same sign are added, then overflow occurs if and only if the result has the opposite sign. So that means if two positive 2's complement numbers are added together and the result is a negative 2's complement number, then the overflow flag would be set to 1. So there is a slight difference between that, and I'm going to show you a couple of examples of calculations where you can see the carry flag is set but overflow hasn't occurred. Okay, so let's have a look at an example next. So example, let's take the example of we want to add up, we've got 8 bits. Okay, so the register is an 8-bit register. So it's an 8-bit register. And it wants to, the calculation that's to be added up is 127 plus 1. And we know that that equals positive 128, doesn't it, in decimal. Now, what the CPU actually does, it will load the register with the bits. So the place value of each of the register bits would be 1, 2, 4, 8, 16, 32, 64 and 128. And for positive 127, that would be adding up all of these. So that equals 127 decimal, and 1 would be represented in binary as that. Now, the most significant bit of both of these is set to 0. So this is the most significant bit of the 2's complement. Numbers is set to 0, which means both numbers are positive. So now we'll calculate them and see what happens. So let's put a line under here and then carry out the calculation. So what have we got? I'll use red for this, just check the thickness. So, and I like to do that so that I can actually see the number. So 1 add 1 is 2. 2 in binary looks like 1, 0. So we put down the 0, carry the 1. 1 add 1 is 2. Put down the 0, carry the 1. 1 add 1 is 2. Put down the 0, carry the 1. 1 add 1 is 2. Put down the 0, carry the 1. 1 add 1 is 2. 1 add 1 is 2. 1 add 1 is 2. Now, we don't have a carry because we have used 1, 2, 3, 4, 5, 6, 7, 8. We've used 8 bits, so there's no carry. But has overflow occurred? Well, let's have a look at this most significant bit of the answer. So the most significant bit is set to 1, which means it's a negative number. And in this case, the overflow flag would be set to 1 because overflow has occurred. So the overflow flag would be set to 1 because an overflow error has occurred. Now, it doesn't look as if there's an error until we, in our own heads, go back and calculate this number. Remember, this CPU is processing at 4 billion instructions per second, so it needs to use these flags to detect these errors because it doesn't have the luxury that the human does of going back and thinking about it for a wee minute. But that's exactly what we're going to do just to get this into our heads. So, in 2's complement, the most significant bit of the range of bits that are being used is always negative. So we're using 8 bits, so that means the 2 to the power 7 place has a value of negative 128. We're not adding anything else to it. Alright, so that means it's negative 128. So if we look at 127 positive plus positive 1 does not equal negative 128. So in our world, in our minds, from our experience of working with numbers, we know this calculation is wrong. This is how the central processing unit works it out, by using this overflow flag and also the carry flag. Right, let's have a look at another example. Example 2. So in this example, what we'll test for is the question, how can you tell if a carry is an overflow error. Now remember what we said for overflow was there wasn't enough bits to represent the answer. Okay, so you were out with the representable range, and the carry flag would suggest that. But let's have a look at this example. This is quite interesting. So let's say that in decimal we want to add -1 plus -1, and as we know in our experience with numbers, the answer is going to be -2. And let's say our register can handle 4 bits. Now, as you know, in modern computers, the registers are 16 bits, 32 bits and 64 bits, but we are just doing it like this to make it easier for ourselves to understand it. So let's write down -1 in 2's complement. So first of all, we'll put down our 4 register bit values. So that will be, I'm going to change my pen, 1, 2, 4 and 8. Now this is a negative, these are negative numbers, which means the most significant bit needs to be negative. So that means there'll be a 1 in the most significant bit. Okay, so let's just put that in there to refresh your memory. So the most significant bit is negative because it's a negative number. But at the moment that says -8, so we need to add a 4 to it, and that will give us -4, and we need to add a 2 to it, which will give us -2, and we need to add the 1. So this is negative, yeah? So that is equivalent to -1 in decimal. And if we add these together, we want to get -2. So let's see what happens. So what we've got, 1 add 1 is 2, and as we know, 2 written in binary is 1, 0, so we put down the 0, carry the 1, and now we've got 1 add 1, which is 3, and a 3 written in binary is 1, 1. So that means we put down a 1 and carry a 1. So we've got 1 add 1, which is 3. So we put down the 1, carry the 1. So then we've got 1 add 1, which is 3. So put down the 1 and carry the 1. So here we have a bit which is out with the 4-bit range that we had. So this is a carry. This would set the carry flag. So this is a carry bit, and it would set the carry flag. And if the carry flag is set, then it has a 1 in it. Now, what does this number actually, in our world, this is 2's complement, remember. So in the actual register, what is this number that's in here? So it's -8 plus 4 plus 2 plus 0, and what does that equal? Well, that equals -2. So this answer is actually correct. So even although there is a carry bit, overflow has not occurred because the rule has not been broken. Now, if you remember, the rule is if 2 negative numbers are added together and the answer results in a change of sign, then the overflow error has occurred. But in this instance, within these 4 bits, the most significant bit is the same sign. So although there is a carry, the overflow rule has not occurred. Now, you'll be saying to yourself, why? Why is this necessary? Why is this important? And if you think about it, let's say we've got a really large number and it's split into 8-bit registers. So that's 1, 2, 3, 4, 5, 6, 7, 8. And there's so it's 1, 2, 3, 4, 5, 6, 7, 8. So there's 3 registers to store this one number. Right? And if you think about what we did up here, so the calculation would carry on in this first register, and then any carry would be carried to the second register. If this first calculation resulted in a overflow error, then that would identify an error early to the central processing unit. But it is possible for something that you think, oh, that's going to be an overflow error, but in actual fact the carry is used in the next part of a register, and that's why both flags are needed by the central processing unit. Now there is a way to check for an overflow error, and it uses a logic gate. So there's a logic gate check for overflow. And what it is, it's the exclusive OR. Now, we've not really looked at exclusive OR, but we do know the logic rule for OR. And the logic rule for OR is, if you're comparing two values, then one or the other, or both, can be true in order for the answer to be true. But in an exclusive OR, only one or the other can be true at that time, not both of them. So the symbol for an exclusive OR looks like that, with these lines representing the values being input and this line representing the output. So the direction of flow is this way. So the inputs into this exclusive OR are the last carry into the most significant bit and the carry. So the carry into the most significant bit is this here. This is what we're talking about. And that was a 1. And the carry at the end is this. This is what we're talking about here. And that was a 1. So in this logic, this exclusive OR logic, that is a 1. And in order for this to be true, that would need to be 0. So because both of them are 1, then this is false. So that's false. So that means that an overflow error has not occurred. So the human had to do this -2 calculation to checked in decimal. -1 plus -1 equals -2. The CPU doesn't have the luxury of that. So if it identifies a carry and it wants to check to see if there has been an overflow error, then it will use this exclusive OR. Good. So here's a question for you. Let's have a look at this, and then we'll evaluate it. So it says a processor uses an 8-bit register to store the results of calculations. State the value stored in the register as a result of adding the 8-bit 2's complement numbers. So let's start with that. We'll make, now you've got plenty of time to do this, so I suggest you do it as well. So we've got our 8-bit register, so we need 8 bits, and we'll put in the values of those 8 bits. So 1, 2, 4, 8, 16, 32, 64, and 128. And the two numbers are 1, 0, 0, 1, 1, 1, 1, 1, and the second number is 1, 0, 1, 0, 1, 0, 1, 0. Now the first thing that we need to identify is that both of these numbers, the most significant bit of both of these numbers, so the most significant bit is negative, because there is a 1, and you know in 2's complement the most significant bit, no matter which bit it is always a negative. Right, so that means in order for there not to be an overflow error, the answer has to be negative, and we need to add these together, so let's do that now. 1 plus 0 is 1, 1 plus 1 is 2, so put down the 0, carry the 1, 1 plus 1 is 2, put down the 0, carry the 1, 1 plus 1 plus 1 is 3, put down the 1, carry the 1, 1 plus 1 is 2, put down the 0, carry the 1, 1 plus 1 is 2, put down the 0, carry the 1, 0 plus 0 plus 1 is 1, and 1 plus 1 is 2, so put down the 0 and carry the 1. Two things have happened here. First of all, we've got a carry bit, and that means that the carry flag is set to 1. And the second thing that's happened here is the most significant bit of the answer is positive. And that means that an overflow error has occurred. So an overflow error has occurred because the sign of the answer has changed from the sign of the numbers being added from negative to positive. So we can say that an overflow error has occurred, and the sign of the answer is positive, and this answer is not 0. So have we answered the question? Well, the first part of the question is state the values stored in the register as a result of adding the two numbers. So here is the answer to part 1. This is what's stored in the register. The carry is not stored in the register because the register is just 8 bits. So for part A, the answer is 0, 1, 0, 0, 1, 0, 0, 1. And for part B, it says state why the value stored in the register is incorrect. It's incorrect because the answer is outside the range of representable values. It's not asking you to calculate the decimal equivalent of these. It's just asking you to answer the question using your knowledge of the CPU status flags and the rules that apply to the flags. Now, during the execution of the calculation, the processor alters the values of the flags. Complete this table. So we've said that the carry flag is set to 1 because a carry occurred. The overflow is set to 1 because we identified the overflow error, and that is that the two numbers being added together were negative and the result was positive within the representable range. So that meant that an overflow error had occurred. This is not 0, so therefore the 0 flag is not set, and the sign is not negative, it's a positive, so the sign is not set. Good.